In this video, I want to talk more about significance testing and model comparison. So we saw in the last video already that we can get quite some different models that use some combination of these predictors. And this is actually quite important to understand because it will help you really understand what's going on when we talk about the p-value, or actually what f-test you should use, depending on your hypothesis. Let's start with a very simple model. Let's say the observed value h equals some intercept. You can draw a head plus error. Now, I did not show this model in the last slide, but this is a extremely simple model that is important. That we often call the null model or the baseline model. As a model where we just have one constant, p0, and no predictive effect on any predictor. Yeah. We can make it a bit simpler and remove the error and talk about the predicted value of h. In this case, the predicted value is only this one intercept. Since the errors have to add up to 0, that means that in this case, this intercept will exactly equal the sample mean. And the errors are the deviances from the sample mean. We talked about it before when we calculate, for example, standard deviation and variance and total sum of squares and total mean squares, because they all look basically at this null model where we just have an intercept only. So let's just describe this as B0 to keep things a bit easier. And I'll make a box out of it to show that this is one model that just includes this one effect. Now, this model has a certain residual degrees of freedom, which basically means the number of free elements in the error terms that we use to estimate the variance around this model. In that case, that would be n minus 1, because we have one parameter, b0. And that would be 5 in this case. And for this model only, we would also call this the total degrees of freedom. And we call the mean square estimate and the sum of squares estimate here the total mean squares and its total sum of squares, because this is the simplest model that you would use. You would very rarely use a model where you don't have an intercept. There's only, for example, if you model differences between time points, then maybe you want to test the intercept. But otherwise, this model is always the least specific model we use. So that's why we call the variance around this model the unexplained part in your data. How much data is there unexplained? In this model, also the total variance or the total mean squares. Now, we can also think of some different models that are a bit more complex. And for example, we can form a model where we have an intercept plus a regression on loneliness, this predictor here. I'll draw a box around this. This model we saw in the previous video as well, which is a line where we predict happiness. So I did not draw predict value of happiness, right? Predict happiness from loneliness. Now we can see that there's a relationship here between these two models. Namely, if b1 equals 0, then this model becomes the exact same model as that model. And that is very important. Now we saw in the last video as well that, not here, but in the other models, that is B0 becomes different, right? It becomes a different estimate. But if B1 is 0, then B0 should be the same as the one in the simpler version. We could have also defined some different models with only one predictor. We could have said, let's do in black, B0 plus B2 times the group membership. I'll just use B2 now, so it doesn't become confusing later. Or we could have done a model where B0 with a head plus B3 with a head times the interaction effect. Now that is not something we would normally do, include an interaction without including also what we call the main effects. But it is something that you could do. And if you treat this as a separate predictor, right, it is something that we could perform. We can see that there are also relationships here. Namely, if this term is 0, right, we get this model. If this term is 0, we get this model as well. The residual degrees of freedom, in this case, for all these three models is n minus 2, or in this case, 4 the residual degrees of freedom. Now we can make it more complicated and include also models that have more predictors. So we could say, make a model, we have B0 plus B1 times loneliness plus B2 times the group membership. All right. In this case, there's again a relationship like this, because if B1 here is 0, then this becomes this model, or this model, right? But if B2 is 0, then it becomes this model. We call a nesting relationship. Now again, we can also think of some other models we could use. B0 hat plus B1 hat times loneliness plus B3 hat times the interaction effect. Or B0 hat times plus B2 hat times the group membership plus B3 hat times the interaction effect. All right, like that. Again, we see relationships here. But now it's like this. And like this. Why? Because if this is 0, then we actually are recovering this model. Whereas if this is 0, we are recovering this model. And the same is true for the other model. Now, we normally wouldn't really do these models where we have an interaction but not a main effect. But it is important to see that it could be done, because it is something that might come back later. Degrees of freedom here, the residual degrees of freedom, equals n minus 3, because there are 3 parameters in each of these models, equals 3. And now finally, we can do our final model, where we have B0 at plus B1, it's a lot nicer, B1 at times the loneliness, plus B2 at times the group membership, plus B3 at times the interaction effect. We can call this the final model. And this model has residual degrees of freedom of n minus 4, because it has 4 parameters, right? 1, 2, 3, 4. Again, there are nesting relationships between these models, like this. Now, why is this important? In the multiple regression framework, and it includes multiple regression, but also ANOVA, we can do 2 types of significant tests. We have, let's do pink, and let's do green. The T test statistic, and we have the F test statistic. And they both do something different. The T test statistic is used to test we use this to test, for example, the null hypothesis that some parameter equals 0 in a certain model. We do this by computing a t test statistic, which is this parameter, the estimated value, divided by its estimated standard error. You don't need to know where that comes from, but the software will give it, the estimated standard error. And this thing has a t-distribution, which is a symmetrical bell-shaped form, with the degrees of freedom that's equal to the residual degrees of freedom of the model that the parameter comes from. So for example, if you have this model, which is what you usually have if you enter all terms, we could do the test and test, is the interaction effect 0? Is this 0? In that case, that interaction effect that we estimate, which is not 0, because it's estimated from data, is put here. We compute t, which by dividing that estimate with the standard error, which we get from software, we get our distribution, the null distribution, and then, for example, we can look at this p-value here for the two-sided test to see if the effect we found, which might have been here, is likely under the null model or not, or likely under the null hypothesis or not. We can use this t-test statistic to try to reject this hypothesis. See, okay, the estimated b value was so strong that we can determine that it was unlikely to occur under a model where this thing actually was 0. Right. And I see I made a mistake here. When we talk about hypothesis, we don't use the hat, because the estimated value might not be 0, but the true underlying value might be 0. When do we use the F-test? The f-test is always used as a way to compare two models. So what the f-test tells us is that the increase in R square, or the increase in explained variance between two models, if that is 0 or not. So basically, what we can use the f-test for is saying, is the increase, the delta, the change in R squared, the explained variance, is that 0? Because this talks about change, this is change, we are always talking about comparing two models with each other. So one thing we could do is we could say, okay, compare this model, compare these two models with an f-test. And that's something we can do. Okay. We compute f by dividing the mean square of the regression we're interested in by the residual mean squares. Let's call it mean square S. So to compute this f statistic, we need these mean squares that are explained by the models. Actually, that's the difference between two models. Let's call this model A and this model B. Then we can calculate the residual sums of squares over both models. And it will always be lower for model B than for model A, because model B is a bit more complicated, explains the data more. So how you get that is you calculate this residual sums of squares of model A, and you do minus the residual sums of squares of model B, and that becomes the sums of squares that we are explaining with the model difference. It really is about the model difference. Then we divide that by the degrees of freedom, which is the degrees of freedom difference between the residual degrees of freedom of model A minus the residual degrees of freedom of model B. In this case here, that was n minus 4 equals 2. So this would be 3 minus 2 equals 1. So basically what it tells us is that this model loses a piece of information into this extra parameter, but is the explained variance that is explained by this model better? Is that worth it? That's the idea. I'll remove this for now. Right, so the f-test is always a model comparison. Now, I said before, these are the total degrees of freedom. The residual sums of squares on the baseline model, the null model, is the total sums of squares. So that's the f-test we saw before, where we're actually comparing this model to this model. Okay, but I'll first talk about this. So here, we're asking the question, was going from this model to this model worth it? Did the explained variance increase? Are we explaining more of our data? The only difference between these models is that we add this B3 term. That's the only difference here. So basically, this f-test is asking the question, did including a non-zero B3 term improve our prediction or decrease our residual variance? The t-test here is asking the question, is this thing 0 or not? Basically, in this case, they're both asking the same question. So this leads to this f-test where we have some critical region. And we try to get a p-value from there. And what we'll see is that that p-value in this case will be the exact same. Which makes sense because we're asking basically the same question. Is this B3, this interaction effect, 0? We're asking it by comparing two models with an f-test or by getting a t-value for this model. Now that's really the important difference between the t-statistic and the f-statistic. The t-statistic is about parameters in the model. The f-statistic is about comparing models. And what we'll see is it will get multiple of these things for each model that we're estimating. Because we can compare our model to many different models to get many different f-tests. And our model might have many different parameters, so it leads to many different t-tests. And these will be important. So in this case, we can use a t-test or an f-test to ask the same question: is this interaction significant? The nice thing about a t-statistic is that we can do a one-sided test. So we can test, okay, only this area, for example, which we cannot do with an f-statistic because it's about variances. So we would use the t-statistic here. So when would we use the f-statistic? The f-statistic, let's clean this up a bit. Oh, that was too much. The f-statistic we can use to compare any model. So for example, we can compare this model, the baseline model with only an intercept, to the model where we have all our terms. And that is what we already did. Then we call this the total sums of squares, total degrees of freedom, total mean squares. And this is our model, and we compare these two. In that case, the degrees of freedom of our f-test equals the difference between n-1 and n-4. So that would be 3, because we add 3 parameters. But here's the interesting thing. We can also compare our model with the interaction effect to something else. So maybe we are not really interested in loneliness. Maybe we want to compare hamsters and cats together, and we are not really interested in that loneliness is also a predictor. So then we want to control for loneliness. So in that case, we would use this model as a null model, where we add loneliness, and we want to see, okay, there's including the interaction effect and the main effect for group. Does that improve the model? And we can do that because it's nested. We can do that with an f-test. And that's something that we will see later on as well. So the t-statistic is for individual parameters, where the f-statistic is for comparing models. If we're comparing two models that only differ in one parameter, they're the same. But if we are comparing models that differ in more ways, we get something else, and we can get a conclusion from the f-test value that, for example, including both B2 and B3 together was worth it. And it could be that that is significant, but the t-values for both of these parameters are not. Because maybe it's really the combined effect of seeing both, that is what is significant. And that is giving you more power. Okay, that's it for these videos.